looking to do better than that. That's why we're also interested in maximum packing, because this is a packing. It hits everyone at most once, but this is not really of all that interest. Finding the maximum set that hit everyone at most once, that's a difficult problem. That's basically what we're more interested in. Okay, so let's move on. Let's see a few more tricks that we can use. I promise you this part is much easier. So where does integer programming come in play? Sometimes you're going to have problems with so-called fixed costs. Or sometimes you'll see them referred to as fixed charges. Basically the idea is this. Let's say that you have a cell phone and they tell you it is, if you make a phone call, it's a cent a cent a minute. I don't know, is that relevant? I haven't paid for a cell phone in quite some time. Anyways, let's say that it's like a cent a minute, right? And they say, okay, it's a cent a minute, but as soon as you place a phone call, you pay $10, which is your fixed cost for the month. If you don't use it, you don't pay anything. But if you use it, you have to. Think about the internet, right? They might tell you, well, you can use that price, like that much per gigabyte, but if you don't use it, you don't pay anything. So we basically have a cost that looks like this. 0, and then suddenly, and notice that I've tried to show that this one is discontinuous over there. Okay? This is typically modeled like that. You have a fixed cost of K, and then you pay per flow. If I build a bridge, right, people are going to pay the toll. If I don't build the bridge, then I don't have that fixed cost over there. So something like that. Okay? It appears a lot in network design problems, flow problems, in general, transportation-related problems. And this is non-linear. So there goes my dreams of trying to solve it efficiently. If only I could render it linear by introducing something extra. And that extra is an integer variable. So this is what we're trying to model. We're going to introduce a variable y, and we're going to say is 1 if x is positive, 0 otherwise. Make sense? So I just need y over there in order to model the fact, basically think of it like a switch. As soon as you pick up the phone and you make a phone call, y becomes 1. Because you've made a phone call. So now I know that you belong to this and not this. This can be easily generalized also if I have this type of costs. For those of you that have taken production and inventory control or a supply chain course, then you probably know this as economies of scale, basically. It becomes a little cheaper as I order more. Or I could also have these economies of scale, right? I could have something like this that says, hey, the more you order, you use up my capacity, so the more expensive it gets. So in this case, you see that I have like multiple different parts. For each part, I can introduce a variable, y1, y2, y3, and I can say y1 is 1 if x1 is between 0 and 100. y2 is 1 if x1 is between 100 and 200, and so on. Okay? So now I can model this, let's name it z. I can model this like this. Do we agree that this and this are equivalent? With the introduction of a y variable like that? It is, right? So now, what I need is I need some constraints on y. I need to force y to become 1 when x is positive. Okay? The very first thing that comes to mind, x is bigger than or equal to y. Well, x is bigger than or equal to 0 anyways. But I also need to somehow tell it x cannot be positive unless y is 1. So I need to have something that says x is less than or equal to blah blah y. Notice that I could not have just y, because then I would force x to 1 phone call per month, right? And I don't have that. Right? I mean, it's not that you make your phone call at the end of the day. It's not Prism, right? It's an actual phone that you want to use for multiple times per month. How many times? We don't know. Could be 100, could be 10,000. That's why we come up with the definition of a big M. Big M is a big enough number that you cannot possibly dream to achieve, but it's still small enough that a computer is going to accept it. So good big M's would be 50, for example. Make 50 phone calls, or 100. But bad big M's would be 3.5 billion. Clearly you cannot make 3.5 billion phone calls in a month, but I mean, it's very big for the computer. Are we in agreement that this models this perfectly? Okay. So this has to do with fixed charges. A different type of trick that we can do in order to model our non-linear problem with linear constraints, because here that's exactly what we did. We turned our non-linear problem into a linear program with, integer linear program. Another thing that we do is the so-called logical constraints. For example, either or. You can choose, let's say that you have 6 homeworks due this week, and you can invest time in at most 2 of them. Then basically you can write xa plus xb plus xc plus xd plus xc plus x hat is less than or equal to 2. So the summation of binary variables basically tells me that it's a logical constraint. Maybe I have an either or. You can either do A or B. You don't have time to do both. Then in that case, I could write something like xa plus xb is less than or equal to 1. Maybe you can do A or B, but only after you've done C. Then in that case, A or B, but only after C. Then basically I would have xa plus xb is less than or equal to xc. And maybe you can only do C if A and B are done. So let's think about that for a second. If only A and B are done, the first thing that comes to mind is something like this, xc with a combination of xa plus xb, right? But that doesn't really seem to work. This one, if I do A and B, this one becomes 2. This one clearly doesn't satisfy that. I could try to play around and put a -1 here, but that still doesn't force it, right? Who can tell me how we can write that? A and B need to be done, and if they are done, then you've done C.
Equality constraint.
How about this? Does that look right? Xc is done if you've done A and B. Are we in agreement? Since xa and xb can only be 0, 1, this is clearly 0, 1. If both of them are done, this becomes 1. If either one of them is not done, this becomes 0.
Yeah.
Problem with this, or are we all happy and we can go home happy tonight? There's a small problem with this, right? Non-linearity. We fought so hard to fix it here. We fight so hard to fix it anywhere we see it. Okay? There is where Forte comes in play. Let me write the name. Forte. It's pronounced. It's French or Belgian. Don't be ridiculous. It's pronounced Forte. Okay? Forte came up with a linearization scheme. And the linearization scheme for Forte, basically Forte's theorem states that any polynomial integer program, okay, so any polynomial integer program, for example, this one, can be linearized. And this is an amazing theorem, even though it's pretty intuitive once we see how it happens. It's amazing because it tells us that if you give me a polynomial integer program, I'm not going to discard it immediately as something that I cannot solve. Instead, I can add extra variables as I go on and linearize everything. The main idea is that you introduce one variable per non-linearity, and then you introduce constraints to force that variable. Let's see the first one. Let's see the easiest one first. Remember, we are in the 0, 1 space, right? Only zeros and ones. So x to the power of 1, 2, 3, 5 is equal to what? We're in the 0, 1 space. Can I have anything else other than 0 and 1? If x is 1, this is 1. If x is 0, this is 0. Can I replace it with this without losing anything else? So there we go. Immediately, from something that looks like this, I went down to this. Still non-linear, but you gotta admit, this is much more easily linearized than the previous version. The second thing from Forte's linearization scheme says the following. If you have two integer variables, x and y, then basically you can introduce a third one, let's name it z, equal to x times y. Now we need to model how z should behave. So, first of all, z is definitely less than or equal to x. If x is 1, z could be 0 or 1. If x is 0, z has to be 0. Same thing applies for y. Furthermore, remember what I did earlier when I was trying to linearize over there? So I said something like this. Z has to be bigger than or equal to x plus y. Clearly that cannot happen, negative 1. So let's see. Does it apply everywhere? If both are 1, then this say z is less than or equal to 1, z is less than or equal to 1. This one says z is bigger than or equal to 1. Hence, z is 1. If x is 0, then this one immediately makes it 0. If y is 0, the same here. Okay? If both 0, then everything kind of works out. Okay? Notice that this one over here would say that z is bigger than negative 1, which comes immediately from the definition of a binary variable. A binary variable is between 0 and 1. So let's really quickly linearize an example. Actually, you know what? I'll let you linearize it yourselves. Actually, you're going to tell me what to do. So let's say that I have x1 cubed times x2 times x3 plus 3 times x2 squared times x3. How can I write it a little simpler? Could I write this? Now what I'll do is I'll introduce a variable for this one. Why this non-linearity? Well, I'm doing that because we see that this keeps repeating itself, right? So I'm going to introduce a variable y23, and I'm going to say y23 is less than or equal to x2, y23 is less than or equal to x3, and also y23 is bigger than or equal to x2 plus x3 minus 1. These are my constraints. Let's name them 1, 2, 3. So now this becomes x1 times y23 plus 3 times y23. Now I'm going to deal with this nonlinearity. This nonlinearity says that x1 times y23. So what I'm going to do is I'm going to come up with a new variable y123, which is less than or equal to x1, less than or equal to y23, and bigger than or equal to x1 plus y23 minus 1. So now in the end of the day, I have this non-linear. This is a very, very useful trick. You'll find it all over mathematical programming with binary variables because it helps us reduce the complexity of the original problem into a linear problem. And the nice thing about linear problems, we can solve them using a linear solver and obtain at least a relaxed version that we can then apply branch and bound and so on. But we cannot do so in a non-linear version. Any questions?
And this is only for 0 and 1, right? I mean, we cannot...
Yeah. This is only for 0 and 1. Nice question. So I can render any integer program into a 0-1 program with many variables as well. So let me show you really quickly how that happens. Let's say that you have xi, which is a number, an integer number, right? Then I could rewrite this as xi is equal to 1 times y1 plus 2 times y2 plus 3 times y3 plus the upper bound, let's say 1,000,000 times y 1,000,000, and the summation of all the yi's has to be 1. Then this one is going to be 1 times 0 plus 2 times 0 plus 3 times 0 plus 4 times 1, hence xi is 4. Ugly, because I introduce a lot of variables, but every integer program can be written as a binary program, every binary program can be linearized, hence every integer program can be linearized. But polynomial. So that applies for polynomials. You cannot expect to have something like this, for example, and say, oh, they are integers, so I can linearize that, okay? You can linearize this. End of story. So in a polynomial, in a polynomial integer program, we can linearize it and make it into a linear integer program with many more constraints and many more variables. Typically, if our nonlinearities are bilinear, like x2, x3, like quadratic, that means we introduce one variable per pair, that is order and squared possible new variables, and we introduce 3 constraints per new variable. Okay? So our problem becomes bigger in size, but linear, and we take that trade-off any day of the week. Alright guys, I'll see you on Wednesday. As a reminder, on Wednesday I'm going to finish class a little earlier, since I'm flying at 6:15. So probably around 4:45, 4:50, we're going to finish with the class. Homework 2 is due tonight. If you have a question, I'll be in my office for at least the next hour, I guess. So just drop by. Okay? All right, thank you.